fraction. Let me simplify one more that has a very special observation to make. Number 34. Right, instructions for something like this would be simplify. Okay? Reduce the fraction. And you know what to do, same thing we've done before. I factor. How's this guy factor?
X plus 5, X minus 5.
Careful. It is one of each, x plus, x minus, because it's the difference of two squares. X plus 5, x minus 5.
5 minus 6.
Now, ladies and gentlemen, if that x squared minus 25 looked kind of difficult to you, you best go back and do some review on factors. That's in my mind, from this point on, that's a given. That shouldn't be much of a challenge to you. When you see the difference of two squares, as straightforward as that, you ought to have it down. Likewise, a very simple trinomial to factor, you ought to be able to do that in 10 or 15 seconds. It shouldn't be a big challenge to you. So if you still need some practice factoring, take some practice factoring. Go back to the factoring section, work every problem there. There's over 100 of them. All right? So pick some and work with them. All right, here's the question. We have factored, and here's where we typically say, aha, common factor, top and bottom. Is x minus 5 the same as 5 minus x?
No.
We said earlier, I think the first time we got together, that there is no commutative property for subtraction because x minus 5 is not the same as 5 minus x. Okay, but here's the question. What is the relationship between x minus 5 and 5 minus x? They're not the same. What are they?
They have the same factors in the
Reciprocals? No. Conjugates. Now stop. That's x minus 5, x plus 5. Change the sign in the middle to get the conjugate. Absolute values. Close. What are they? By the way, add them up. What do you get when you add them up?
same thing. No.
I'm sorry, what? They're opposites. That's right. You add these guys up. What's this? Take x minus 5. Okay, I'll take it. And add to that 5 minus x. What do you get? X minus x. We got it here. 5 minus 5. I get 0. What do we call numbers that add to 0? Opposites. These are opposites. They don't look like opposites. Opposites typically look like 7, negative 7. You change the sign. Well, in essence, that's what we've done. Doesn't quite look like it, but in essence, that's what we've got here. Now, I'm going to be asking you in days to come to recognize opposites. X minus 5, 5 minus x. A minus b, b minus a. Notice they both have a minus in between. You just switch the two values. Well, let me ask you another question. From the 6th grade, or if the 6th grade was traumatic, let's move up to the 7th grade. If you had that configuration and you were asked to simplify, would you say, well, can't go any further here because those numbers are not the same? What would you say that's equal to?
1.
What would you say?
Negative 1.
Negative 1, right? You'd say a number over its opposite equals negative 1. You'd be absolutely correct. So here's the conclusion we arrive at from this observation. I can cancel opposites if I leave behind a factor of
Negative 1.
Negative 1. Okay. So I can cancel these opposites if I leave behind a factor of 1. So what I do, I canceled the opposites and introduced the factor of negative 1. Why? Because a number over its opposite is equal to negative 1. And you could write this like that, or you could write it just negative x. Either one of those would be sufficient. But here's the thing you're going to either recognize or not. Hey, if you didn't recognize those were opposites, you'd say, I'm finished. Those are I'm through. There's nothing common top and bottom. But if you do recognize them as opposites, you will cancel them, introduce the factor of negative 1, and simplify that expression. Okay? So I will be asking you to recognize opposites. Notice what they look like. The x and the 5 are just changed. They both have a minus sign. All right, let's go on. Let's introduce the concept of multiplication. Now, let me just remind you. Can I multiply those two fractions? How many think I can? Absolutely can. Yes, you're right. I can multiply any fractions at all. All right? So I can multiply any fraction. You don't have to have the same denominator to multiply fractions. How do you multiply fractions?
Get the common
Straight
denominator.
across. You don't cross multiply. That's like that. You multiply straight across. Numerator times numerator. Denominator times denominator. I'm finished. All right? That's the old mathematical thing you're familiar with. I can multiply fractions, you betcha, multiply them straight across. What we're going to look at now is the multiplication of rational polynomial expressions. So we're going to introduce polynomials here. We're going to do the same thing. Let's look at number 49. Here's a concept that's helpful when you're multiplying fractions. If I'm multiplying fractions, I really don't need two fractions. I can simply make this one big happy fraction. Okay? It's just everything in the numerator and everything in the denominator. So I'm looking for common factors, top and bottom. If I wanted to factor it, I can certainly do that. If I do, I see probably a little bit more clearly what those common factors are. I got an x minus 1, and I got a 5, right? So that's my answer, right? 5 times x minus 2? Is that right? That's not right? What's the problem? That's in the denominator, right? This is in the denominator, so let's keep it in the denominator. Always an understood remaining factor of 1. So don't lose sight of that. Which probably makes you think that one of the wrong answers on the multiple choice would just be 5 times x minus 2. Hey, you multiplying fractions? Factor everything on the top, factor everything on the bottom, look for common factors, write them out. And then simplify. Let's do another one. How about 53?